Max Potter from the University of Manchester. I'm a PhD student studying solar flares. My current research is about energy release in solar flares. And another interest of mine is nuclear fusion. Firstly, I'm going to be telling us about why we need alternative forms of energy production. Then I'm going to talk a bit about what fusion actually is and how we're working towards achieving it. And then finally, the problems along the road to getting it. The global demand for energy is expected to increase by more than a half from 2010 to 2040. Back in December of 2015, members of the United Nations Climate Change Conference met and agreed that by the second half of the 21st century, we need to be emitting zero net carbon emissions. To satisfy rising energy demands, as well as meet these climate change targets, we need radical new sources of power that are clean and safe. Current options are traditional nuclear fission power, which is unfavourable because of radioactive waste and concerns about safety. Another option is to look at renewables, such as solar or wind. Unfortunately, the problem with renewables, such as wind and solar power, is that they aren't reliable. They don't produce a constant amount of energy at any given time of day. So, traditional nuclear power stations are fission power stations. This means that they split up heavier atoms into lighter ones and release energy. But the opposite process can also happen. This is called fusion. Fusion is where you take lighter elements, fuse them into heavier ones, and release a significant amount of energy. This is the process that powers the sun. Fusion is preferable to fission because we have plenty of the fuel, there are fewer environmental impacts, and there's no chance of a dangerous meltdown. Fusion is the power source of the sun. It requires very extreme conditions. So reproducing these conditions on Earth has proven to be quite a challenge. We need to reach millions of degrees Celsius so that when the fuel particles hit each other, they have enough energy to fuse. And we need a very high density so they hit each other very often, which increases our chance of getting a successful fusion reaction. We need to subject our fuel to the conditions found in the core of the sun. This means it's going to be incredibly hot. So hot, in fact, that the atoms rip apart into smaller pieces. These pieces are charged particles. What this means is that we're in a different state of matter. We're not a solid, a liquid, or a gas anymore. We're a plasma. A plasma is like a charged gas. It can conduct electricity, and it can be controlled with electric and magnetic fields. So, examples of plasma that you might be familiar with include lightning storms, neon lighting, and the northern lights that you see in the sky. So we've got our fuel, and we've heated it to the conditions where it becomes a plasma. How do we contain something that hot? It'll melt any box that you try and put it in. So we have to come up with a solution. Thankfully, it being in the plasma state and being composed of charged particles, we can control where it goes using magnets. And currently, the most successful method of containing such a fusion plasma is called the tokamak. The tokamak is a donut-shaped container that uses a series of magnets to force the plasma to stay in a certain region. So I mentioned that the magnetic cage that we're going to be creating is donut-shaped. Why is that? Well, there's something in maths called the hairy ball theorem. This is the reason why coconuts have a tuft on the top of them. If you've got something roughly ball-shaped like a coconut and you try and comb it, there's no way of combing down the hair and making it smooth everywhere. There's always going to be a tuft from it. Whereas if you've got a donut and you comb that you can comb that completely flat all over with no tufts whatsoever. So we've got our donut-shaped container, and currently we're building the biggest one in existence in the south of France. It's called ITER, which stands for the International Thermonuclear Experimental Reactor. It's a €13 billion project the cost of which is being shared by nations all over the world. And it's aiming, when it switches on in 2020, to produce 10 times more power than we give it. So if we're to achieve this, there are a lot of problems that we have to overcome first, in the form of instabilities. This is where the plasma, our fuel, interacts with the magnetic cage in a way that's not desirable. It can result in some of the fuel being thrown out and damaging the container walls. Energy release and particle acceleration in solar flares is not very well understood, but we know that it is similar to the process which controls instabilities in tokamak plasmas. So, by writing computer codes that simulate the interaction between the charged particles in the plasma and their containing magnetic field, either the loop structures on the Sun or the donut-shaped cage in the tokamak, we hope to understand how these explosive events can occur. And if we do, we'll have a sustainable source of energy.